You've probably heard the word commutator thrown around a bit in quantum mechanics. Today we'll have a look at what commutators are, and we'll illustrate how they work through a basic example. Before we get to that, however, let's go back and have a quick look at what operators are and how they work. In classical physics, we define dynamical variables. These variables give us information about the system. So in one dimension, we have the direction x, the momentum p, and the energy E. When we move them across into quantum mechanics, they become known as operators and they serve a slightly different purpose. So from the examples here, we can see that x just still remains as x. However, p becomes the momentum operator, and that's defined to be negative I h bar d over dx, where I is a complex number and it's the square root of negative 1. H bar is reduced Planck's constant, which is simply h over 2 pi, and d over dx is obviously the derivative with respect to x. Also, the energy E moves over to I h bar d over dt. So now that we have established a relationship between them, we can get into more of the details about what they are and what they mean. So to do this, we'll illustrate it through a basic example. Firstly, let us define a new operator. So our new operator will be d over dx. Now by itself, d over dx has no meaning. We can't take the derivative of nothing. Hereby comes a rule with operators. Whenever we place an operator, it's always in the expectation that it will be followed by some function. So in this case, let's follow it by some function f of x, right? Now, this expression right here does have a very well-defined meaning. It is simply the derivative of f with respect to x. Before we get to defining what the commutator is, let us look at one last property of an operator. So normally when we deal with scalars, we know that they commute. By this, we mean take some number, a, and another number, b, then we know that a plus b is equal to b plus a. We are simply swapping the order at which we add these two numbers together. So these commute. However, with operators in quantum mechanics, they generally do not commute. What this means is that if we have two operators, say A and B, where we use the hat to define the fact that they are an operator, then generally they do not equal to the reverse, BA. Essentially what this means is that if we move both of these terms on the left hand side and the right hand side of the equal sign over to one side, then we will get the expression AB minus BA, which is non-zero. Therefore, it becomes convenient to define the expression known as the commutator. This is written using the following shorthand notation. So we have square brackets with our first operator followed by our second operator, and they are separated by a comma, which is defined to be that non-zero term which we had before. So, in words, this is simply the commutator of A and B. We also know that since the commutator consists of operators, and that operators do not commute, we have the following relationship. The commutator of B, comma A is in fact equal to the first operator multiplied by the second minus the second multiplied by the first. But this is simply the negative of the first term, right, which is equal to the negative of A, comma B. One other important fact to note down about operators is that you cannot equate them to other operators. For example, A being equal to B does not mean anything, right? So we saw an operator before which was defined to be d over dx. Essentially, if we define B to be something like d over dt, for example, and A to be d over dx, then we're saying that d over dx is equal to d over dt. Clearly this has no meaning. We can't take the derivative of nothing. Going back to what we mentioned before, we always write an operator in the expectation that a function will follow up, right? So it's always going to be just before the function. In quantum mechanics, our function that we deal with is the wave function, psi. So we write the function is equal to psi. Therefore, what we will be seeing is the following. If we have some operator A operating on the wave function psi equal to B operating on psi, this does not mean that A is equal to B. It just means that the result of the operation of A on B is equal, of A on psi is equal to that of B on psi, right? So, for example, using the definitions above, this will imply that d over dx of psi is equal to d over dt of psi. By no means is this actually correct with respect to an electron or a photon, etc. However, that's essentially what it means. It means that the operations acting on psi are equal, not that d over dx is equal to d over dt. Alright, just keep that one in your mind. Now that we have gone through the formal definitions, we should be able to power through an example. This should really show how operators and commutators behave. So let's define two new operators. Our first operator will be simply d over dx, and our second will be x. Now, if we want to find the commutator of these two operators, which is given in shorthand notation by the following, then we expand it out, right? So it's going to be the first operator multiplied by the second minus the second multiplied by the first. However, the problem is that we have this d over dx operating on nothing here. This means that, going back to what we just did, we have to multiply our commutator by the wave function. So doing this gives us comma x multiplied by psi, the same expression as above, dx x minus x d over dx, except we're going to multiply these by psi, right? And this is going to give us d over dx x psi. Here you have to be careful. The operator on the left is going to operate on everything to the right, not just x, right? And then we have our second term, x d over dx of psi. So expanding this out further will give us psi dx over dx plus x d psi over dx minus x d psi over dx. Clearly we can see that these last two terms will cancel out, so we can eliminate these straight away, and we're left with this term. We see that, oh, it's a bit wonky, but anyway, we see that dx over dx is simply equal to 1, and thus we are left with the following equation. The left hand side over here is simply equal to psi. Now if we divide through by psi, we find that what we initially wanted to calculate, which was the commutator of d over dx and x, is simply equal to 1.